Welcome to the final project where you're going to design a Wilkinson power divider using multi-stages. So let's go ahead and get into it. Um, this is the article that talked about how you design your multi-stages. I had sent this to you, so this is where you get your coefficients from. We are going to use an 0805 set of resistors where the gap between the pads is 1.2 millimeters or 0.47 inches, 47 mils. Okay. One of the things that I'm going to ask that I was having trouble with and I found a workaround is when you start a new project. So let's just say I'm going to start a new project, and in the past I've said, oh, go ahead and start create a circuit. I'm going to ask you to, the first thing you do is go ahead and create an HFSS 3D layout, just a blank project. And you're going to select the library. Now, just to let you know, I did update the library. So if you want to, you can download it off the Google Drive. The links are in the YouTube videos. You're going to select that. And the reason you need to do this is we're not going to use this, but it loads up the planar via element so that now you can properly use the ground pads. And then from here, you would go ahead and create a new, your circuit, and you would continue on from here. So I'm just going to say that's the first thing you're going to do, just load up a blank 3D layout project and then go on to your circuit, okay? And the other thing too, as we mentioned, I'll just really quickly, so your options, you're going to want to know your default units wants to be inches, know where your directories are, your personal lib, your project, and your syslib, and then also verify that in your layout editor that in other that is checked. And in display, it's 100 mil and 50 mil for the grid, and this is your drawing extents. And under snapping, your targets are vertex, edge, center, and grid. This is the square, the triangle, and the diamond. So make sure it looks like that. Okay. All right. So let me go ahead and I'm going to open up the project. I'm not going to go through step by step like I did before. I'm just going to open up the one I did. And essentially what you're going to do in this project is identical. You're going to mimic exactly what I'm doing here. So I'm not going to obviously show you all the steps like have you download the project, but I'm going to walk you through it to give you some hints. You should have all the information you need to design one, but let's go ahead and walk through the steps. So essentially this is what we're going to design, and is a multi-stage Wilkinson power divider. And if you look at the top, so you come in here and it separates into two. These are called radial bends. So you make these two radial bends for your stage one, or this is actually going from right to left will be stage one. So this is your first R1 and then Z1. This is R2 and Z2 relative to the paper. If you use the nomenclature of the paper, they call this R1 and then Z1 and then R2, Z2. But you're still using these radial stubs. And you use a whole bunch of these little bends and things to go from a single input to two outputs that are exactly 0.5 inches apart. The reason why I do that because the connectors line up real nicely. So you're going to want to try to get your connector launches at 0.5 inches, and then the board length will be whatever it is. So let's go back to the very beginning, which is the ideal Wilkinson. So you start off a circuit, and again, remember I said you've already loaded a blank HFSS 3D layout project. So here we have a single stage Wilkinson, and here's a dual stage. Again, these are the coefficients from the paper. They calculate your Z1 impedance, 60 ohms, your R, your resistor value, 265 ohms, and then your second stage Z2 is 83 ohms, and then the fixed resistor is 93 ohms. And then you're going to implement this in Microstrip, okay? And then there's a reference. So let's go on to the Microstrip version, and I showed you a picture of it, but let's go ahead and break it down. So this is the schematic that you're going to actually implement to create that layout. It's pretty complicated, so I'm going to go back and forth a couple times so you get a feel for it. All of the elements you need are already here. So let me just point out the elements. Let me start there. Component libraries, you're going to go to distributed, and you're going to go to Microstrip. So you are going to use the Microstrip physical length, MSTRL, and you're going to use them like here. Here's a couple of them here, and then there's a few of them there. You're also going to use the MST, which is found under general components. This is the reference plane T-junction with a reference plane at the edges, right? You see that one. You're going to use that one here, 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 and then here and here. So you're going to use that in 5 places. You're also going to use this radial bend, and the bends are found right here. So here is a radial bend right there, this bender, MS bender, and you're going to use 2 of them. It's 90 degrees. So you go from here 90 degrees to there, and then 90 degrees back. So you're creating a semicircle, and again, you're doing it on both sides because this is a symmetrical device. And you're going so this is Z2, and you're going to do one for Z1 as well. A couple sets of bends that's going to make that semicircle. What else are you going to use? Well, so here we have, these are mitered bends, and that's also found here. It's a 90-degree bend, and the edges are mitered, and that's to get you from this point back up to this radial bend. So you'll use 2 of them here. That's the mitered bend. And you're going to use, again, you don't have to do it this way. This is the way I did it. I'm just showing you what I did. And this is an arbitrary angle bend that's found right here. It's similar to the mitered bend, but you can change the angle. Here the angle is fixed at 90. This angle can be anything, so I'm choosing 45 degrees. And then we have a couple of straights, and we're 45 degrees back, right? And then we have a straight, we have a mitered, the same mitered bend, and then a straight section. So I just showed you where they are. They're under general components for the T. Bends has the radial bend and the arbitrary angle bend and the miter bend. And of course your transmission line segment is found there under Microstrip and distributed in the Nexum component library. Okay, so let me break down this a little bit more. So let me go over to the layout portion and kind of show it to you there, maybe easier. So we're starting off and we have a straight section. Right here is the T. We go into 2 small straight sections. The purpose of these 2 right here is to separate this so that we have a fixed gap. Remember I said we're using an 0805 resistor. From that point to that point, zoom in here, from here to here needs to be 047, and from here to here. At any point in time, if you're in this part and you want to measure something, what you do to use the measuring tool is you go Layout, Measure, and you scroll in and you pick it. So the triangle is a vertice, and finish. And you go down here to the start and the stop, and you can see that it started at plus 0.0235 inches. Just show you the it's in inches, and then minus 0.0235. So this is centered, the whole circuit's centered around y equals 0, and then that point to that point is 47 mils. So we have achieved that gap. Now I've already done this, but you're going to want to tweak these 2 lengths here so that this gap is 47 mils and this gap is 47 mils. Okay, so that's the first tweak you're going to do. Is you're going to adjust these lengths to make these 2 gaps 47 mils. What else are you going to tweak? Well, the distance from here to here wants to be 1/2 inch. So we go measure, and just to verify that, click here, go to this vertice, get the little triangle, right click, finish, and you can see, yes, plus 0.25 to minus 0.25 are the actual points. So that tells you, yep, that is 1/2 inch. That's good. You're also going to want to know the overall length of the circuit. You use the same tool by saying Layout, Measure, and click right. And the length of this guy is 1.31 inches. Now yours is not going to be that. You're going to have to tweak it. So how do you tweak it? Well, you tweak it with these 2 lengths. These are this P launch variable, and I'll go through them. But that's how you're going to adjust the overall length. Is you're going to tweak these 2 these launch variables. So that's the only tweaking you're going to do. The only optimization you're going to want to do is the radii of these 2 angle bends. Everything else is going to be pretty much held constant. So again, going through this launch, a T, and these 2 points. So let's take a look at the schematic. And again, this circuit is symmetric, so from here up is the same as from here down. So I'm only going to look at half of this guy. And then, so let's go ahead and zoom in. What do we have? Well, we have port 1, we have this launch. It's got a length of P launch and the width of WZ naught. What's WZ naught? It's 51.8 mils. We have the MST. It's going to tee off into two directions. Here's that little gap piece of transmission line called P gap. Here's your two radial bends. Now, to get an idea of, you really want from this point to that point to be 90 degrees. You want these to be 90-degree sections where the impedance is Z sub 2, right? So Z sub 2 is 83.35 ohms. Using the calculator, I've calculated that it should be 17 mils wide, and the 90-degree length at 2.5 gigahertz should be 670 mils. So since this is a semicircle, right, this semicircle means that the radius should be the linear length as far as the circumference divided by pi. That's the circumference of half a circle. This gives me an estimate of what R sub Z2 is, what this radius of these bends should be. It's about 213 mils for Z2, and then Z1, same kind of thing. If you go through 36.7 mils gets you 60 ohms. 648 mils is 90 degrees at 2.5 gigahertz. Divide that by pi, gives you the circumference that's equivalent. So 648 divided by pi would give you a 206 mil radius for these guys as a good starting point. Again, we're going to optimize that later, but it gives you an idea of what to type in. For the fixed resistors, again, we said we're going to use 085 from DigiKey. These are the closest values I could find to there, and we'll go ahead and order some of those up. So again, going through this circuit, we have the launch, the T, this little section. We have two radial bends, back to another T. Now notice on this T, this one port I have is W pad, and that's the width of the pad that's going to go to the 085, and that W pad should be 47 mils. Do I have it? Yeah, 47 mils. That's the width of the pad right there, and you'll see that. Then we have another chamfered 90-degree bend, another set of radial bends, another T. Here's the 45-degree bend, sectional line, 45-degree bend. This is the vertical section, a right angle, and another vertical section. So if you take a look at that, and what I would recommend doing, honestly, is just pausing the video to get an idea of what's on the screen. So everything you need is right here on the screen. You can just pause the video. So let's go ahead and take a look at the layout again. So this is how you do it schematically, and here is the layout. And you can see all the components, the two different pieces here, your two radials. Here's your T, here's that right angle chamfer mitered bend. Here's two more radial bends. Here's another T. Here's the 45-degree bend there. Here's a straight section, another 45. Here's the vertical straight section. Here's the mitered right angle, and then here's the final launch. Both symmetric on both sides. That's the complete layout. So this is the final layout, and again, this is the schematic. Okay? So you're going to implement this. If you're feeling daring and you want to do this for a 3-section, go for it. It'd be challenging. I think we're only going to require you to do this exact 2-section. So yeah, and just to optimize, I mentioned optimization. So you right click on your circuit, you hit design properties, you'll notice that we're only going to optimize the radius for Z2 and the radius for Z1, those radial bends, and you'll put your initial values that you guesstimate here and give it a range, and you're going to optimize each one of them. So you selected two variables, right? Just so we're clear, R sub Z2 and R sub Z1, we're going to optimize both of them. When you go to your optimization setup, what are we doing? Well, we're going to select S11 between 2 and 3 gigahertz. So the challenge is going to be, can you optimize this over some band? I'm arbitrarily saying, let's center it at 2.5 gigahertz and try to go from 2 to 3. It can be anything you really want, but let's use that as a target. And you want the S11 to be less than 25 dBs or better than 25 dBs, and you want S21, the insertion loss of one of the legs, between 2 and 3 gigahertz to be greater than 3.3 dBs. Okay, I'm weighting this one a little bit higher, so I put a little bit bigger weight there. So just as a side note, let me just look at show you what the results of the ideal when we have the single and the double. So let's see, do I need to recalculate? I probably need to recalculate that. Go back to ideal, analysis, right click. Oh, I guess I don't have to, it's already done. All right. Okay, so here is the single stage. This is the red and then this blue. You can see it's pretty narrow band. Here's the two stage. You can see it's wider. And what you're going to do, you're going to try to optimize it between 2 and 3 gigahertz. But notice in the ideal case, you can achieve exactly 3 dBs at the center frequency, because in the ideal case, there's no losses. There's no imperfections in this schematic. However, when we go to our microstrip line version, this monstrosity here, and we look at the results, we get this. So it's already down to 3.3 dB, so we're getting several tenths of a dB loss in the whole circuit because of, again, losses, and the fact that there are losses are creating this instability. So you're not going to get a perfect even 2-stage or 3-stage. The losses will kind of throw you out a little bit, which is fine. That's kind of what the whole point of this exercise is. But yeah, so if you go to the optimization, as I mentioned, you're trying to optimize both of these parameters. And then, so if you were to do this, right click and say analyze, then it should jump around and try to attempt to achieve those. Now this is where you're going to spend your time, is trying to figure out how to achieve to change those values to get the best response you can. And again, part of this is due to the fact that there are losses in the system, and this is your overall schematic. Okay, so you're all done that, right? And you say, all right, I'm done my circuit. I've laid it out, and so now what I'm going to do is copy this. You go right click and you say copy, and you go up here and right click and you say paste. It makes a copy of this project, so you can kind of start from here. And that's what this guy is, PCB layout. It's literally a copy of the project. Same schematic and everything. When we go to the layout portion though, here's where things get a little tricky. Okay, so what I did is noticed, like we did the last time, this first element here, I said, oh, fix it at so here's 0, 0 of my printed circuit board. Remember we talked about that crosshatch. I'm putting this 10 mils in because we want a 10 mil gap around a whole printed circuit board. This yellow part is the dielectric. So I'm putting this circuit in 10 mils. You press Control M, if you remember, that kind of resets everything. But then you have to adjust these two launch sites, these two launch lines right there. I think we call it P launch, so that you make the whole length of this some given length that's nice and uniform and even. I think I already did this. Let me just look at the schematic. What did I do? So I checked in my schematic. I have P launch. What's P launch here? 198.605 mils. So I've obviously done this so that the whole overall length of the circuit is an even number. And if you look up here on this guy, I've made this vertical section 92.231 mils. Now why did I do that? The reason why I did is, if you go back to the schematic, to the layout, I wanted these two to be exactly a ½ inch apart. And the way I did that is I tweaked these two sections, move them up or down, and that moves these launch points either closer together or further away just by adjusting these two sections. So that's how I adjust. So again, this launch part, it's by definition set at 10 mils at 0 right there. Everything else cascades along, and I can adjust the length of this by tweaking these two P launch sections. Okay, now these launch sections want to be about 200 mils long, because remember these pads right here, from here to here, that's 140 mils. So you need to have some buffer. These cannot be that close to the line. You don't want the ground pad to interact with your transmission line, so you want some buffer here. So I think my default was 200 mils, but I tweaked it a little bit. And then, yeah, then I adjusted these two based off of everything else to make these 0.5 inches. And again, how do I know what they are? Use the measuring tool, layout, measure, and then I can measure the distances between any 2 points. So that's what you're just sit there and iterate through that. When you get to this point, you're going to add these components to it. So let me go ahead and just, I'm going to delete them to show you how easy it is to add them. Once you had this section and you've kind of got it all to where you want it to do, you go view. We did this before, but I'll just show you again. You go to the library, and I think I call this, it's the same part, I called it connector lib, it doesn't really matter, but you're going to add the ground pads element. You bring it over here and you snap this one to the vertex here. Okay, then you bring another one in. I hit R to rotate it, and I'm going to snap this guy to here. And similarly, one more. Okay, now here's why I told you to do the HFSS 3D layout blank tool. For some reason, if you started your project with just a circuit element, those vias don't show up at all. Even if you did exactly what I just did, those vias wouldn't show up. You needed to start your whole day with basically, when you first initiate your project, you have to add a blank HFSS 3D layout project. And when you do that, it brings in, I know it's kind of a goofy thing, but by doing that, it brings in, if you go to layout and via style, it makes sure that this planar EM via is part of your project. You do that first, and then you won't have any problems. So let me go back to here. So now we have the whole basic thing here, and all you got to do now is put in your dielectric layers, like we had done before. And this can only be tricky because you have to kind of draw them in. Let's see here. It does PCB layout. So yeah, so let me go over here and look at view layers. So let me turn off some layers. So there's our top layer. You draw this guy in. This is just one of these squares that you draw in, and you got to set the width to be a 10 mil gap around any metal. Here's the bottom one. This is also just a square. So remember, all the metals, including the green bottom layer and the top layers, have to be 10 mils recessed in from the edge of the dielectric and the outline. So if you turn off, so I've made this outline. Now remember, the outline, it is done with 4 separate lines. If you remember from last time, this outline is not a box. You start from here and you literally go, I'm going to start, you just kind of draw a line like this, and like this, and like this, and like this, and like this, right click and finish. And then you go through and you say, oh, it's got to be a 0 width line. I know I talked about this in the last video. And then you line up these points to line up with the outline or the dielectric layer. So don't forget that otherwise you won't get the right outline layer at the Gerber file level. So that's the outline layer. And you have the dielectric in the bottom, just like we did before. And then 2 other things we're going to do differently. So let me let's leave this on. Let me look at the solder mask layers. Hopefully they're still there. Oh, good, they're still there. Let me look at the top layer. Okay, so I'm only putting on. I'm going to put the outline layer on the top, and here's the top solder mask. So what I'm doing is wherever I draw, now the solder mask layers have to be closed blocks defined by 2 points. But what I'm going to do is wherever I draw a block, see here's a block here, and by the way, the solder mask layers can go beyond this outline layer, just for convenience of drawing. Wherever I draw this box, there will be no solder mask in it. So imagine that I'm filling this box with the lack of solder mask, because it actually at the board shop does a negative. So there's going to be no solder mask here, and then I put another box right here, and there's going to be no solder mask there, which means the only place on the top layer that there's going to be solder mask is this little corner down here, because I haven't done anything there. And then what I put there is my silk screen. Remember we talked about, so you can scratch or in some symbol or some whatever, but if the silk screen, for it to show up, according to Oshbark, you got to put silk screen on top of solder mask. So we have solder mask here, and I put my silk screen on there. That's the top layer. To do the bottom layer, let me turn them off, and let me turn on the bottom solder mask. So the bottom solder mask, I'm going to do 2 blocks, and the only thing you really have to make sure there's no solder mask in the bottom layer is the launch points, because you need to solder to the ground plane for underneath the launch points. This underneath the board, again, now we're looking at the bottom layer. I'm not looking at the top layer anymore. So this is the bottom layer. I just need this to be free of solder mask. This can have solder mask on it. Who cares? So, and it will. So it'll literally have solder mask from that point all the way to this point, and no solder mask here. Why did I do that? Because if I wanted to put some silk screen, I could do that. So what do you notice? So here's some silk screen, but I've written it backwards. So, and the reason is when you drew your Gerber files, when you draw it, you're drawing like you're looking transparently through the board. So if you want it to show up correctly on the back side, you have to write it in reverse. Hopefully that makes sense. So when you put all the masks together, this is what you get. Again, the top mask, it has this part and this part. And I have some Wilkinson, like some lettering down here. And if I put the bottom solder mask, there will be no solder mask here or here. There will be solder mask and silk right there. Okay. So that's all you have to do with those layers. We talked about the outline layer, that kind of goofy thing where the outline is, click on the right one, is defined by 4 points. All these other ones are all defined by the 2-point blocks. And I think that's pretty much it for defining the whole circuit board. At this point, when you have all this done, you can generate Gerber files right from here. You don't have to go to the next level because you've defined each of the layers. You have your, so just kind of go through it real quick. You have your top layer, which is defined by your traces. These are defined by your circuits, and the vias should be in there if you've added that 3D layout project. You have your dielectric layer. By the way, this doesn't do anything. It doesn't generate Gerber files. It's just there when we take it over to HFSS 3D layout. It's just a dielectric layer. That will generate a Gerber file. That's the bottom layer. That's the green. And then you have, of course, your outline, which is the same basic shape as your dielectric layer. This is all from previous videos. And then we're doing something a little different in the silk. So we have silk on the top, silk on the bottom, and your solder masks. And then from here, so just to let you know, I did generate Gerbers. The way I did it is from this layer, from this project, I just went File, Export. First I did the NC drill file, right? And let's put this in Wilkinson divider. Now, here's a convention I am going to ask you to do. It'll make it easier for you. So give it a name. We'll call it Wilkinson divider underscore, and for the drill file, make it _8. All right. And then you say OK. And now from the same thing, you're going to say File, Export, Gerbers. Same kind of thing. You're not going to put anything there. You just say Wilkinson divider. It'll figure out the underscores later. Save. And here, what you want to do is, I'm going to delete these so we're going to show it again. Add 7 pages. The first page is going to be silk screen top. Silk screen top. That's number 1. Number 2 will be solder mask top. Number 3 will be top layer. You notice we're literally going from top to bottom. The next will be bottom layer. Okay. Then will be bottom mask, solder mask bottom, and then the 6th one will be solder silk screen bottom right there. And then the final one is the outline. So we're literally just going from the top of the circuit board to the bottom. It's going to generate 7 Gerber files. The first one will be silkscreen top, silk solder mask top, the top metal layer, the bottom metal layer. The solder mask bottom is 5. 6 will be the silkscreen bottom, and then finally 7 will be the outline. You say okay. Now, the reason why we're doing that is, and we talked about this before, but I'm just going over it again. You go to Wilkinson divider, and so what it does is automatically creates these underscore 1, 2, 3, 4, 5, 6, 7, 8. So now all you have to do is change 1 Gerber to this 1 GTO. We talked about the extensions last time. And then 2 Gerber goes to 2 GTS, 3 Gerber change to GTL, number 4 Gerber change to GBL, 5 GBS, 6 GBO, 7 GKO, and then finally 8 will be your drill file. So there's going to be 8 Gerber files generated. You can use KiCad. So I just took what we just did and brought it into KiCad, and you can take a look at the Gerber viewer in KiCad, which is the free software, and you can make sure it's all done correctly. And then you can do what I did, which is to upload it to OshPark. So here I uploaded those to OshPark, and what's kind of neat about OshPark is it literally gives you what the board should look like. So the top board should look like this, where lower left-hand corner has a little bit of the solder mask. Their solder mask is purple. And then here's my top silk, and here's all the metal. And then my bottom would look like this. This will be gold. Here's the solder mask, like I said, and see how the back is now, it's shown like I'm looking at the bottom from underneath. This is looking at the top from top. So this tells me, it's like a design rule check that, yeah, these were done correctly. And so that's kind of a real quick overview of what you're going to be doing. Of course, then when you're all done, to look at this from HFSS 3D layout, what we're going to do is that we're going to turn these guys off. We don't need these in HFSS 3D layout, right? We're only going to need these 3 layers. So to generate this one, I'll go through it real quick. We're going to highlight the board. Again, we just have the 3 layers here. Okay, we're going to highlight the board, and we're going to say edit copy into HFSS 3D layout. And of course it creates this guy, and we've done this before, but I'll just do it real quick. So the only thing you're going to do at this point in time, you're going to add your connectors. So you remember that how we brought in this connector to it. Remember, this is our SMA connector guy. Let me just close all these windows. So what you're going to do is, we're in the HFSS 3D layout. We press this, we hit copy, go down here and say paste. It brings in one of the connectors. I'm just going to move this out of the way for now. I'm going to paste another one. So that should be port 1. Oh, I didn't do that right, did I? Let me try this again. Copy. I press Control C, Control V. Yes. That's 2. And then we do the same thing, Control C, and then Control V. Yep, and then to orient these, you click on them, you go, I want them to be 180 degrees. Now, there's a reason why I'm going through this, because I wanted to show you one other thing we have to do. So we're going to line these up a bit. We have to add the resistors in, so it's really straightforward to do, but I figure you're going to want to do the simulation, so why not? You got to go through this little extra step. So we're going to put the connectors on. We have to line them to the edge of the board, not to the edge of the copper. Okay, so we got our connectors on there. Now, how do I put resistors in here? The way you do that is you Control D centers it. Okay, so you're in this window. I'm going to right click and say select edges. I'm going to go here and I'm going to select that edge. I'm going to select this edge. I'm going to right click and go boundary, create RLC. Okay, and let's do the same thing here. I'm going to put a resistor there to there, right click, boundary, create RLC. And then, so what that did is that created internal ports. Go select back, Control D. Now I'm going to double click on this guy, and under EM1, I'm going to say R enabled. I'm going to enable a resistor to happen there. And now when you click on it, under EM design, I can actually put a resistor value there. And so I think that one is the 93.1 ohm. That's R2. And then here, double click. Actually, you don't even have to. You do it right here. You click on that, you say click R enabled, and then that one's going to be the 267 ohm. So what do we just do? We just put in from there to here 2 ports that you're going to put a lumped resistor of 93.1 ohms here, and there from that edge to that edge 267. So when you rotate it, you can see that I've actually put, what you're actually kind of doing is putting like a thin film lumped resistor right there between those 2 edges. See that? That's pretty cool. Although we're going to do it with an SMT resistor, but still, so that's how you do that. And then you would finish up the project just like you normally do, which is you here's your boundaries. You add an excitation. Oh no, that's right. We have to do the thing where you click on all these guys, if you remember, and you right click and you go, ports, create ports on components, no net, bam. And so now your excitations are there. Yeah. Analysis, you click on that, right click and go add HFSS setup, advanced, 20 times. This is all from before, there's nothing new. And then of course you got to say, 10 megahertz to 4 gigahertz, and step size is 10 megahertz. And so now you're ready to go, except for one thing. You're going to remember from last time, you click on the project, right click, go down to design settings, and you have to go to meshing methods and uncheck enable design level intersection checks. You have to uncheck that, otherwise you'll get errors. Now I can click on this and go, let's look at a validation check, and it goes through and wait till you get all the green check marks. Of course, it actually does kind of an initial pre-mesh of both the connectors and the board just to make sure everything's copacetic. So it goes through and does that. Should be pretty quick, generally speaking. And then hope my computer doesn't crash. Let me pause it while it's doing that. All right, it's done. And yeah, so all you'd have to do now is you click and right click and you say analyze. But I'm not going to do that because so there's the board. There's the whole thing with the connectors, with your resistor, and you can simulate that in HFSS 3D layout. So it's pretty cool. I think that's about it. I may upload this project later, but that would kind of be cheating if I did it right now because it would kind of give you the answers. But hopefully that's enough to walk you through. Go ahead and give me questions, or send me emails if you have any questions. Thanks a lot. Good luck.